Hey everyone, welcome back, and today let's solve Leetcode problem 3408 titled Design Task Manager. So this is quite a long problem statement here. Just to kind of quickly summarize what exactly the problem wants for us. You guys can feel free to just pause the video and read through this problem statement yourself. But effectively, we're just trying to maintain a dynamic set of tasks where each task has a user ID, it has a task ID, and it has a priority and support. Right? Effectively, the add method, which would take in those three parameters, would add a new unique task ID. The edit method would simply update the priority of an existing task. The RMV, taking in a task ID parameter, would simply remove a task, and the exec top method would basically just execute, remove, and return the task with the highest priority. However, if they were tied for the highest priority, it would be the highest task ID to tie break that kind of tie, right? And it would simply return the user ID or -1 if there were no tasks, right? And so exec top is not going to actually have any parameters, right? Of course, except self, which is kind of like that base parameter, right? So effectively, how are we really going to solve this problem? Just a kind of a quick kind of overview of how we're really going to go about it. Effectively, we're going to be using a max heap implementation using the heap queue module, right? And the heap entries are going to be tuples of length 4, right? They're going to have a negative priority, they're going to have a negative task ID for the tie breaking part, and and on all those kind of ties for the highest priority, the task ID and the user ID, right? That kind of ordering is very important because the highest priority has to come first for sure, and then for ties, the highest task ID has to come first, so that's going to be first and second respectively for those two values, which kind of leads us to that main observation that we really need to make, in the sense that by pushing the negative priority and then the negative task ID and then the task ID and then the user ID, we can also both order by priority and task ID and still actually carry that kind of original task ID and user ID for validation when we're actually returning them in the RMV and exec top methods. Right? Now we're also going to have a dictionary called tasks, which would actually map our task ID to a tuple of length 2, which would be a priority, and the user ID that would basically just store the current valid state of any task for that specific task mapping. And whenever we actually edit or RMV for those two methods there, effectively we're just updating or deleting that dictionary, right? And all these heap entries would become stale, if you will, when they actually no longer match our tasks, meaning we have to actually handle those stale entries with something called lazy deletion, basically just skipping them when they actually are popped, similar to what we did in yesterday's problem as well, which was the September 16th, August of 2025, right? And effectively, the main observation for this that we can really make, kind of tying back to yesterday's problem as well, is that lazy deletion actually completely avoids the need for an expensive heap item removal operation, right? We're effectively just trading extra memory or these stale heap entries for more simplicity and asymptotic efficiency. Right? Now, why is this solution kind of going to work? Well, basically, the reason why is because every valid task is going to have at least one heap entry that reflects its most recent priority, right? Whereas the stale entries are always going to be ignored when they're popped, right? That would also give us that efficient time complexity of log n per the heap push pop kind of operations for the heap operation complexities, and constant or big O of 1 for the dictionary updates, which is really good for hash map and hash set. So they're very efficient data structures in terms of lookup additions and all those operations with them like that, right? And to kind of just skim over the examples and input constraints here, effectively we're just given the initial object and we're just calling these different methods here, and our output would be null 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 for the null return type methods, or we're simply just returning the tasks with the highest priority, so in this case would be 3 and 5, right? And that's really it. You can guys kind of just read through the constraints here, but all the constraints say is just kind of confirm what the problem statement tells us, and they're just kind of confirming that we're always going to have valid inputs, if you will, right? Which brings us to the actual coding part of the solution and how we actually implement that kind of a logic into, well, the actual software. Right, so the first thing that we're going to do is actually initialize our initial data structures and methods and variables and whatnot in our init constructor in this class here. And the first thing that we're going to use is going to be the self.heap data structure, what we kind of talked about in the problem statement, right? Or rather self.tasks, so sorry about that. right? And effectively, the whole point of this self.tasks method here, basically, it's going to be an empty dictionary that maps each task ID to a tuple. It's going to have a priority and it's going to have a user ID. And whenever we actually add or edit a task, we have to update this dictionary. And whenever we remove a task, we have to delete the key, right? Which kind of just allow for quick validation of our different heap entries, right? And so this self.tasks here, effectively what it's going to be a dict, right? Or a dictionary in Python. And in this dictionary, we're going to have an integer as the initial mapping and a tuple. More specifically, it's going to be a tuple of length 2 of 2 integers, right? And this is going to be equal to an empty hash map here, right? And that's really just kind of the main kind of part in this solution. Now, what is the other data structure that we're going to be working with? And I technically could have reversed this order, but effectively that's going to be the self.heap, right? And the self.heap here is going to be of type list. In this list in Python, and this is going to kind of be how we format it, it's going to have a tuple, in this case of length 4. And every single data type of all of these 4 parameters, or tuple values, if you will, are going to be of type int. And we're going to initialize that to be an empty, you guessed it, list. Hence why we initialize it with a list. And the whole point of this heap data structure here, or this initialization of this instance attribute self.heap as an empty list, is we're effectively treating, or rather, we're using heap q to treat a normal list as kind of like our heap container, where we're simply just type hinting to use these 4 different integers because we know it holds 4 element tuples of length, or rather of type int, right? And effectively, the whole point of this structure is simply to hold the current and stale task entries, right? And that's really it for our data structure initialization in the init constructor for this class. Now we have to actually begin looping over our input list, right? And in this case, it's going to be looping over each triple, or kind of triple bond, if you will, in the input list. So for every user ID, sorry, I think ID should be capital, or rather, I think it's lowercase. For every user ID, for every task ID, and for every priority in our tasks input array, effectively, we're just looping over, again, each bond of length 3, if you will, or over each triple in our input list, if you will, where this constructor is simply just going to call add for each incoming task so that we reuse the same add logic and heap/dict invariants. Right? Effectively, we're just unpacking this triple into 3 different iterators, or 3 different parameters, if you will, of user ID, task ID, and priority. Now, for every iteration in this kind of for loop here, we're going to first call the self.add, so self.add, and we're going to pass in the 3 parameters, user ID, sorry, I keep forgetting that it's not capitalized, task ID, and the priority. Effectively, for each of these initial triples here, we're just calling this add method, or more specifically, this self.add method in this class itself, to actually insert it into the self.tasks data structure. And then we're actually pushing the appropriate tuple onto the self.heap data structure. And basically, the whole point of reusing add is to keep the constructor simple and to keep it consistent and more efficient, at least in terms of lines of code. Which really just concludes the whole point of this init constructor method here. Now we can move on to the add method here, right? And the whole point of this add method here is basically just going to register that new task, right? It's going to guarantee, in this problem at least, that task ID is unique on add. And so because of that, we don't have to actually check for any collision in this method. We simply just annotate the return type as none. Since we know we don't actually return a value, we're simply adding a method that registers a new task. And the first thing that we have to do is record the current state of the task in the dictionary. And the way we do that is by actually accessing the task ID mapping. And so what we're going to do there is we're going to get self.tasks, and we're going to get at the specific index, if you will, task ID, right? And it's going to be equal to the, again, tuple of length 2, priority, of the priority and the user ID. We're effectively inserting or overwriting the task ID key in self.tasks with the length of 2 tuple of the priority and the user ID, right? Which basically just makes the dictionary reflect the current priority for that specific task ID. Now, if this task ID already existed before that, which technically shouldn't be on add, it would actually update it, right? Now, what we have to do after that is actually push an entry to the heap so it actually participates in the exec top method order, right? And the way we would do that is by basically just heap q.heap pushing would be the kind of syntax for that in Python, and the first parameter that when we always push is actually passing in the data structure that we're pushing onto, or in this case the heap that we're pushing onto, which would be self.heap, and we're going to push onto this heap, again keep in mind a tuple of length 4. It's going to be in this case the negative priority because we want it to act as a maximum heap, not a by default minimum heap in Python. We're going to also for that same reason pass in the task ID, and we're going by priority or by order of importance here, then the task ID, and finally the user ID at the end. Effectively, we're pushing a 4 tuple or 4 length tuple, if you will, onto the self.heap, where the priority has to be negated, so the larger priorities are popped first. The task ID also has to be negated, so the larger task IDs win in a tie, and the task and user ID, basically we just want the original ID for the quick validation and deletion, and the user ID so we can actually return it on the exec top method. Or again, we're including those both negated values for the actual ordering and the original task ID and user ID for correctness. Right? Now, that's going to conclude what we have to do for this add method here. That brings us to what we have to do for the edit method. And keep in mind, these two methods here at the end are going to be a lot, or rather, these three methods at the end here are going to be a lot longer, at least when compared to the first two methods that we just did. Right? So the first thing that we're going to have to check here is to actually verify that the task ID already exists in our task list, right? And so what we're going to do first, and to kind of reiterate what the edit method does, basically is just changing the priority of an existing task, and that's really all you really need to know for the edit method purpose. Now, how we actually check that case is if task ID is not in self.tasks, and again, we kind of briefly glossed over this like 10 seconds ago. Effectively, we're just kind of having a safety check to verify that task ID exists in self.tasks. Now, technically, this problem does guarantee that it does actually exist, but, you always want your code to be defensive, if you will, right? In case callers are always, going to be wrong, and so you always want to just cover for this case just in case, just for the sake of it and just for best practice. Now, if it isn't found, of course, we obviously have to just immediately return, because if the task ID is not found, we simply have to just exit early. Again, under these Leetcode constraints for this problem, this won't happen, but it's still clean to kind of just include this guard in your code as well, just honestly, even for best practice, if nothing else. Now, here we actually have to retrieve the user ID for this specific method call. So I'm going to call it user ID, and it's going to be self.tasks, and the key that we're going to pass in is the task ID, more specifically the task ID at index 1, right? We're effectively retrieving the user ID currently associated with this specific task ID from that authoritative dict, where self.tasks at task ID would be that tuple of length 2 of the priority and the user ID. But since we only want the user ID, index 1 is going to give us that user ID, and so we have to pass in index 1 of that task ID tuple of length 2. And we're going to need this user ID when actually pushing the updated entry to our heap. Which brings us to the next part of this code here, which is to actually overwrite that authoritative record and push a fresh new heap entry, right? And so what we're going to do to kind of counter that, or rather handle that, is get self.tasks at that specific task ID and set it equal to a new tuple of length 2 to be the new priority and the user ID. Right, we're effectively just overwriting the dict entry here to reflect that new priority, which makes the earlier heap entries for this specific task ID stale. Why? Because their priority won't match self.tasks. We no longer care about them. They're called stale heap entries at this point. Right, that's kind of like the main observation that you really need to make from this kind of solution here. And finally, we then have to actually push that new heap entry with the new priority onto our self.heap. And so again, we're going to be using the heap_heap push operation here. And the first parameter is always the actual data structure that we're pushing onto, which in this case would just be self.heap. And we're going to push onto it a tuple of length 4. Again, we have to negate the new priority again, just to make sure it's in the correct order of importance, where the highest values are popped first. The negative task ID, the task ID itself, and that original value more specifically. And finally, the user ID. Again, we're simply just pushing that new heap entry with the negated new priority and the negated task ID, where it will, now the heap is now going to contain at least one entry that matches the authoritative dict for this specific task ID, which should basically just be the freshly pushed one. Now, that brings us to the RMV method here. And again, the whole point of this RMV method here is really just to simply just remove a task by task ID, where again, the main observation there is that we're actually implementing the lazy deletion tactic, which is basically just deleting from the authoritative dict, and we don't have to actually remove the heap entry directly, right? That helps us with our runtime complexity a lot, right? That kind of lazy deletion method, right? So the first thing that we're going to do is first check, okay, is task ID actually in our tasks? basically we're just checking the dictionary to see if we actually do have that task currently existing in our tasks, and if it does, we have to delete it, but if it doesn't, well then we really don't have nothing to do or anything to do, right? We have absolutely nothing to worry about. Now, so if it is, we first have to delete it, or using the del keyword here for this data structure hash map here, self.tasks at the specific task ID index. We're effectively just deleting the key task ID from self.tasks to make any heap entries for this task ID invalid. Where basically the future exec_top method would just skip them. And that is really it for this RMV method here, actually relatively short. And finally, that brings us to the exec_top method here. And this is actually going to be the long, really lengthy method here, and the longest one by far. And so this is where you have to really sit down and pay attention here. The whole point of this exec_top method here is really just to find and execute the current top task with the highest priority, and then of course the tie break with the highest task ID, and then to remove it from the system and return its specific user ID. But however, if there are no valid tasks, like the problem says, we have to return -1. Right, so we have to pop basically until we actually get a valid current entry and skip all the scale entries. Right, so the way we're going to handle this is while self.heap is actually non-null, meaning while there are still entries in the heap, because we use lazy deletion, some of these entries still can be stale, and so we have to actually validate every single entry that we actually pop. And the way we actually pop from the heap is using four variables, because again, keep in mind, every tuple is going to be of length 4 in the heap data structure. So we're going to have a negative priority, we're going to have a negative ID, we're going to have a negative TI, or rather a positive original task ID, and we're going to have an initial UID, right? Effectively, this is going to be the user ID, task ID, negative task ID, and negative priority, and it's going to be basically just heap q dot heap popping from the top of the heap. In this case, we only need one parameter, and that would be the data structure that we're popping off of. We're simply just popping the smallest tuple from the minimum heap because we stored negated priority, and we also stored negated task ID, which is basically just the smallest tuple corresponding to the highest priority and the highest task ID in the original values. We're simply unpacking into these 4 different variables, neg_p, neg_tid, tid, and UID, and basically just using those from the popped entry here and storing them and their corresponding values accordingly. Now, once we actually pop or extract that topmost heap entry from the heap, we'll get current to basically just be self.tasks.get, and then we're going to pass in the TID here, right? And effectively, the whole point of this here is basically just popping, or rather after we pop it, we're basically just getting that authoritative current record for that specific TID or task ID from our self.tasks data structure. And if this kind of line here, or this case, if it actually returns none, that means the task was removed or it never actually existed as current, right? And in either case of that being the case, that means the popped entry would be stale, and so we have to skip it, right? And so basically we have to then get the reconstructed original priority from that negated value. And the way we do that is setting p, our actual priority, to be -p. Right, because we have to convert that -p back into its original positive priority by negating it once again, because p is a priority that actually the popped entry actually claims to be, right? Its absolute value, if you will. Now, if the current that we actually retrieved from the self.tasks, again, if it was none, like we talked about like a few seconds ago, that means the authoritative record is actually missing. The task was removed by the RMV method here after this heap entry was pushed, and so that means this entry is considered to be stale. And so if this entry is stale, that means the task was removed, and so we have to just continue on to the next heap entry. And so we just have to really just type in the word continue, right? Because we have to skip to the next iteration of the while loop here to pop the next heap tuple, just to check if that's also stale or not, to see if we can actually work with that. Now, if current was not none, meaning we didn't actually fall into this conditional, that means we aren't working with a stale entry. Right, that means we have to actually unpack the authoritative tuple of length 2, the priority and the user ID, into the current priority and the current user ID, or the current P and the current U. Right, so now if current P is equal to P, and the same thing applies for current U and U, for the UID, that means we're simply just checking if the popped heap entry exactly matches that authoritative current state, where the same priority and the same user ID hold true. And if both of them match, that means this heap entry would be the correct current top task to actually use and return for this exec_top method here. And so if it is actually a valid top, we'd have to remove it from the authoritative dictionary and return it into the actual user ID, right? So effectively the way we do that is actually to del self.tasks. at this specific at the specific task ID or TID, basically just deleting the executed task ID from the self.task so that it's fully removed from our system to basically ensure that any future exec-top calls method here will not consider this task ID and effectively just return our UID once we're fully done with that solution. Right, so basically just returning that user ID of the executed task, which would then end our exec-top method from this return statement. Now, if we don't actually return any user IDs from any calls of this while loop here, we'd return -1 at the end of this while loop here, basically just to indicate that there were actually no tasks to execute, which would map exactly what the problem kind of specifies in the description as well, right? So unless I made any syntax errors here, they should be accepted and there should be a valid solution. So let's go ahead and hope that that works. Okay, so let's go ahead and see what I did wrong here. If current p. Okay, so I forgot an equal sign. That is very silly of me. Again, just simple syntax errors here that could cost you here, and many mistakes like that. Let's go ahead and see what the error is here. Okay, yeah, so probably just a really simple, really simple task, or rather, error in terms of like, let's see. Self.task is equal to dictionary. Yes, we're passing in an int and a tuple of 2 ints here, and we're setting that equal to, let's go ahead and see. Object does not support assignment. So I don't exactly know what the issue is here, at least in the core issue. This doesn't really make sense. So let me just kind of reverse the ordering of this and see if that changes anything here. Go ahead and run this. And this is just me debugging my really faulty code here with simple logic errors here. Go ahead and fast forward this part here. I will put that in the description probably. But yeah, this code actually does get accepted on Leetcode. I did submit it like a few minutes ago before actually recording this video. And so I will paste the full solution as well. But yeah, let's just go ahead and see what the error is here. So self.heap is equal to a list. Okay, so yeah, I should be using colon. I should not be using an equal sign. Very silly of me to make another very simple syntax error like that. Let's go ahead and see what else is missing here. Current p is not defined. So, did I miss something here? Yeah, I clearly, very clearly missed something here. I have to actually declare current p and current u, with the current priority and the current user ID to simply just be the current value itself, right? Which we actually extracted from our self.tasks method here for that specific task ID. So now this should be an accepted solution. I know I've been saying that quite a lot, but now this should be accepted. And now, as you can see, this really is just about as efficient as you can get it to be. So again, on a high level, how are we really solving this problem? Effectively, we're just maintaining two structures. We're maintaining a heap that produces the candidate top tasks in big O of log n time per push and pop operation. And we're also maintaining a dictionary that stores that authoritative current state for each task ID. Now, on the add and the edit kind of methods here, we're simply updating the dictionary and we're pushing a fresh heap entry each time. And on the RMV method here, or the remove method, we're simply deleting that dictionary entry. And finally, on that exec top method here, we're simply popping from the heap until the popped heap entry actually matches our dictionary, which means it's actually the current version of that task. And if it does match, we remove it from the dictionary and we simply return its user ID. But if there aren't any valid tasks left, we simply have to return -1. Where again, that main lazy deletion approach keeps operations simple and they keep them efficient, while also guaranteeing that we're fully correct and precise, which leads us back again to that main observation that you really need to make to solve this problem in the most efficient way possible. Every time we actually edit a task, we push one more heap entry. And if a task is edited many times, there may be multiple stale entries for that specific task ID, but each stale entry has to be popped at most once, and so the cost is going to be kind of fully amortized across all the operations, right? So that brings us to the final part of the solution here, which is going to be the memory and runtime complexity. So the overall runtime complexity here is going to be an actual fully simplified big O of k log k, right? We're simply just letting n be the number of currently stored tasks, m being the total number of heap entries across the lifetime tasks, and of course typically m is going to be equal to n plus the number of edits, right? And so for the actual adding method here, it's going to be a total kind of complexity of big O of log m. For the edit kind of method here is going to be a fully simplified big complexity of log m. For the RMV method here, it's going to be constant, right? Because heap entries are kind of lazily ignored later, and we're just simply deleting from that method here. And the exec top method is going to be big O of k log m, right? Or k log k overall, if k is our initial tasks. And for the memory or space complexity, a lot more simple. It is really just linear or big O of m, where m is simply, again, tying back the actual total number of heap entries across the total lifetime kind of set. Right? Again, it's a total number of heap entries created across the lifetime solution, where typically m is going to be equal to n plus the number of edits, right? Why? Because the self.tasks data structure is going to hold big O of n entries, or the current tasks. The self.heap is going to possibly hold up to m entries, where m is going to be the initial pushes plus every add plus every edit. And so worst case, like when the worst case possible, the memory complexity would be big O of n plus edits, which would really just be simplified to big O of m, right? Now, if these edits are actually bounded, the heap size would be big O of n, but the overall memory or space complexity is really just big O of m. Right, so if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.